doctor and what is required to actually achieve this sort of a feedback. Because in terms of implantable artificial kidney, we have to constantly monitor the parameters of the patient that happened during the renal replacement therapy. And specifically, we need to be aware of what particular parameters of blood can be changed during the interaction with the implantable artificial kidney. Because in case of the renal replacement therapy, it's crucial to actually evaluate the efficiency of the method in terms of blood filtration. So just to remind from, just a small reminder from the previous lections, the core idea of the implantable artificial kidney is basically not just imitate the native nephron, but to get closer to the idea of the constant blood filtration, just like it happens in natural kidneys. And in that regard, we need to make sure that the clearance, for instance, the parameter that can be evaluated for the mass exchange units or rather glomerular filtration rate is actually adequate in case of the implantable artificial kidney. That in fact we achieved some parameters that are required to imitate the natural kidney. Yep. 1 second, I constantly forget to switch it on. So the basic idea, yeah, there is a little shift of the letters, just don't mind it. So if we have the artificial kidney system and we have data that we receive from sensors, and for instance, since we interact directly with blood, we need to basically evaluate the concentrate of some essential nutrients or some toxins that are presented in blood. So we can evaluate, for instance, the clearance of this particular substance. Usually it's creatine or urea if we want to evaluate the elimination of small-sized solutes. And just a small example how it happens, for instance, in the conventional hemodialysis, if we have the mass exchange unit, the dialyzer, and we have, for instance, the blood flow, and let's consider we don't take into consideration, for the simplicity reason, we will not consider the ultrafiltration because otherwise the blood flow will change right at the beginning of the mass exchange unit and at the exit. And we have the dialyzer flow. Usually the most common parameter to evaluate the clearance of, let's say, urea is to use the following formula. It's basically the multiplication of the blood flow on the concentration of the substrate urea on the inlet of the apparatus minus concentration of blood of urea blood in the outlet, and there will be a concentration of this substrate in the dialyzer flow on the outlet. And basically, in order to evaluate this parameter, you need to measure this concentration during the dialysis procedure, or you need to take into consideration that you need some sensors right at the beginning of the blood flow, at the exit of the blood flow, and at the exit of dialysis fluid flow. Usually, development of the urea sensor is a very complicated topic. Well, there are industrial urea sensors. There is still a big challenge to create this same sensor for the medical application and for the application and specifically in dialysis. So it's one of the technical issues that have to be resolved in terms of the implantable artificial kidney. And taking into consideration that we need to miniaturize this apparatus in order to implant this device into human body, and we need to make sure that there will be no discomfort, no severe interaction between the apparatus and the internal organs. We need to miniaturize the sensor itself. So we need to find the approach how to measure essential parameters like the creatinine, for instance, concentration, or urea concentration, or if we observe some nutrient concentration, it could be glucose concentration sensor, etc. So we need to make sure that we apply an appropriate method that allows us to miniaturize this sensor without affecting the ergonomy, the overall size of the implantable kidney. In terms of the feedback, we need to take into consideration that we need to collect the data from the artificial kidney. So we need the processing of the data that we acquire from the artificial kidney. We have to combine this data and provide a certain data analysis and data preparation in terms of there is some disturbances or signal changes that have to be filtered. So, and we have to organize the feedback between the clinician and the patient, of course, because patient is the biological system that directly interacts with the artificial kidney. It's not just we have to acquire the data from the device and look of how the urea concentration will change right at the in the entrance of the microfluidic system and at the outlet of the microfluidic sensor. It's not just we have to control the molecular parameters of the blood. We also have to control the state of the patient himself. So the patient has to provide the feedback to the clinician. And it's not just mean that we collect the data only from the device, but we collect data from the patient and from the state that he experiences right now. So this is basically the feedback concept, a very simplified feedback concept that includes the biotechnical system, the artificial kidney with the set of sensors that provide us some basic information about the molecular parameters or the ultrafiltration flow, the sodium concentration, etc. This is millimole per liter, it's a typo. So basically, if we talk about this parameter, it's actually millimole per liter. I apologize for this typo. Yeah, let me just address a small example that was implemented within our university in the Institute of Biomedical Systems. So basically, that's a feedback example for the glucose monitoring. So this particular measurement is required for patients who suffer from diabetes, and usually when they control the glucose concentration, they require the invasive methods that basically prescribe the blood sample collection, and then this blood sample is applied to the substrate with the enzyme that decomposes this glucose and changes the opacity, the optical opacity of the solution, and then this particular chip is inserted in the glucose meter or sensor, and this is how the patient has to constantly control the glucose concentration. The disadvantage of this method is basically the fact that the blood collection procedure is quite uncomfortable for the patient and can be painful. The reaction of the skin can be quite predictable. In that case, the skin can become harder and it will be harder to collect blood samples in some time. So the sort of a golden brow of the glucose sensor would be a non-invasive approach that does not require the blood sample collection, and basically a type of sensor that could continuously monitor the glucose concentration in a patient's bloodstream. And basically, speaking of the feedback example, since there are a lot of complications with the glucose measurement, like a simple error that can occur during the glucose measurement can provide inaccurate data for the sensor, and that can lead to the wrong decision to, for instance, infuse the insulin. And if there is just an error of the glucose, so there is a spike of the glucose concentration, and the patient injects the insulin, that can be a very dangerous situation for the patient. So basically, there should be a monitor and the some feedback with endocrinologists that basically acquire statistics, and they adjust the work of the system, and he adjusts the interaction with the patient. And this telemedicine example actually consists of the sort of biotechnical system that includes of course, the biological system. In our case, it's a patient with diabetes. He has the glucose sensor that continuously acquires the data about the glucose concentration. This information is sent to any external device, such as smartphone. The insulin pump has the sort of a feedback loop with the patient and the glucose method, and he acquires the information from the glucose sensor directly from the smartphone. And of course, in this particular case, there should be a direct, some sort of indirect control of the endocrinologist or the specialist who actually understands the of what exactly is happening, or what kind of data we collect, and how to adjust the work of that system in case of this glucose monitoring. So just to explain this idea, because if we talk about the implantable artificial kidney, at some point we have to control the glucose concentration as well. And basically, if we talk about the conventional methods of the glucose concentration control, they usually require some sort of an enzyme to decompose the glucose on some components that change the optical properties of the solution. That usually a very expensive and method or way of product these sensors, that basically leads to the complication that we need to immobilize enzyme on the sensor, and we need to control the stability and the activity of the enzyme, but we need to control the glucose within the microfluid system. So if we want to combine the optical method with the enzymatic method, we need to take into consideration that the enzyme has to be a very long-term stable enzyme that can work for years. Usually it's not the case. If we exhaust the concentration of the enzyme, that means that the glucose sensor will not be working the way how it's intended to work. So in that case, a different approach is required, basically the approach that will not rely on the enzyme or any other complicated and expensive technique. And basically this measurement should be we have to create a sensor that can operate within the human organism, and it can provide an accurate data for a very long time. So basically, there is an optical approach that relies on the fact that we have the change of the absorption spectra for the glucose at a certain wavelength that does not actually experience any interference from the other substrates that can disturb the signal from the glucose. And basically, the main idea is to choose the parameters of the glucose sensor exploitation that will not be interfered by any other metabolites or any other substrates or solutes that or solutions in that case, if we talk about water, because the main type of solution in blood is actually water. That's the type of fluid that dissolves any substrates and works as a form of transportation of this solid in the blood system. So basically, yeah, the main idea revolves around this optical approach. And that's the implementation in the laboratory setup, how we can implement this particular system. So basically, this is a type of sensor that can be potentially obtained and adapted to the implantable artificial kidney. We have the laser diodes, and we have the photo detector sensor, and we have the object. In our case, the biological object will be the patient's blood, or it could be, if we talk about the proximal convoluted tubal imitation system, we deal with the ultrafiltrate, and we can actually monitor this glucose concentration in the filtrate itself. So basically, we can monitor both blood and the filtrate in case if we properly calibrate this system to the appropriate biological object. So usually in this experimental setup, we use the quartz tubule and we pump the solution that imitated blood or any biological fluid that exists in human organism, and we obtain the data like the we had to control the temperature of the sensor, because if we talk about the diet, any shift in the temperature can lead to the fact that we obtained the distorted results. So we had to cool down this system. The main problem with the approach that we use, that this particular system requires a cool down. And in terms of the implantable kidney, it might be not the case that we will be able to somehow monitor the temperature of this case. So we need to change a sort of the sensor that will not heat up during the work within the system. So the temperature here was quite crucial, because it could affect the temperature of the laser diet and photo sensor that received the signal from the laser diet. And in terms of the biological object that we monitor, we have to observe the temperature and the other parameters within the system. And in case of this project, we actually made the blood plasma glucose non-invasive monitoring using the diffuse reflectance spectroscopy. And basically, that's the way how this system operates. So there are a lot of microcontrollers. There is a lot of system that we actually receive from the biological tissue. This particular sensor was adapted to soft tissues that we can apply the sensor to. And basically, there is the idea that the reflection of the signal to the photodiodes can provide us a good information about what particular optical properties we receive from there. And we can recalculate these parameters to the glucose concentration. And basically, that's just one of the examples how these biofeedback loops can be implemented. If we talk about the implantable artificial kidney, of course, we have to take into consideration we need to apply specific data sensors to this implantable kidney. That includes the glucose, and the glucose concentration can be measured by non-invasive optical methods, because we do not have a privilege to use the enzyme method in that particular case. It's a little bit harder, or rather it's a big challenge to monitor, for instance, the nitrogen-bound toxins. And one of the main markers that help us to evaluate the clearance or the glomerular filtration rate of that system, if we talk about the artificial kidney, we can apply some sort of an analog of this parameter. So we can monitor some sort of a parameter that will be close to glomerular filtration rate. And basically, we can do it in a clearance manner, or we can just readjust the formula that we used for the native nephron, but just apply that to microfluid system that provides us with the initial primal filtrate that we basically work with in a proximal convoluted tubule next. So one of the main sensors that has to be taken into consideration will be urea sensor. So urea concentration control will provide us some idea of how fast we eliminate other particular small-sized molecules like creatinine or uric acid or bilirubin, etc., and so on. There is like that has to be what has to be taken into consideration, that even if we talk about the small-sized molecules, those that are usually smaller than 500 daltons, or in molecular mass it will be 500 grams per mole. So it's like basically urea that will be 60 daltons, or yeah, let's rewrite it in the more mass. Creatinine that will be about 113. Uric acid that will be 169 grams per moles, etc., and so on. Even if we talk about nitrogen-bound toxins, for instance, urea is basically the smallest substrate here, so we will have the different permeability for this type of substrates, and creatinine, for instance, will have a little bit smaller clearance in comparison with urea, and uric acid will be even smaller because the permeability will be changed due to the fact that the diffusion will get smaller the bigger molecule we have. Nevertheless, if we, for instance, have the opportunity to monitor one of those parameters, and if we know that urea, for instance, is a small size molecule because it's smaller, some parameter that we describe as the small size molecule, then we basically are confident that other toxins will be removed from the system as well by the same means. And why urea is basically so prominent marker in a conventional dialysis, because it's usually very easy to obtain the sample and to measure the urea concentration, for instance, by enzymatic method. There are multiple approaches how to measure urea, and basically it does not require some very expensive equipment like chromatography. It actually requires the biochemical analyzer, which is a photosensor, and a few enzymes to perform a couple of reactions that will allow us to measure the concentration of the urea. But that's the laboratory test. So in terms of laboratory tests, it's usually very easy to a metabolite that's very easy to control. In terms of the implantable artificial kidney, we have to develop a biosensor or any sort of sensor that can monitor urea in a continuous way, and we will not require to extract blood from the patient, so we can monitor the working system within the human organism, and we will acquire the continuous data about how the concentration of this particular metabolite changes during the renal replacement therapy. This is a small part of my bachelor's work. Evgenia Klyazhova, she was working with urea control methods, and basically she summed up the sensor types. I need to emphasize that basically it's not like a spectrometer or enzymatic method or a chemical method. The enzymatic method will not be able to implement it without the additional methods that will allow us to measure additional properties of the solution. For instance, if we talk about the potentiometric method, this is a very good article that covers this idea. If we just decompose the urea by means of hydrolysis on the components like ammonia ion that basically change the working potential of the electrode, and we did not apply any additional method to actually measure that difference, the enzymatic method on its own is just the hydrolysis. So we need some additional method to control such parameters, for instance, as the working potential of the working electrode. And from this potential, we can basically calibrate this system to specific concentrations of this urea. And we can apply the combination of the biological, of the potentiometric method with the enzyme attached nanoparticles, and thus we will be able to control the urea concentration in the solution. So when we talk about the enzymatic method, we have to emphasize that we actually apply this particular method to something else. It could be a photosensor or a working electrode if we're talking about the potentiometric method, or 3-electrode system if we talk about cyclic voltammetry. And basically why enzymatic method is so desirable in that case is because if we just apply the potentiometric system, and we try to measure how the potential is changed in the presence of urea. Since urea is a neutral molecule, it does not have any charge, it's obvious that there will be no significant effect or no effect at all on the parameters of the sensor. So the idea behind the biosensor lies within the idea that we amplify the hydrolysis of urea in the presence of the enzyme that we immobilize on the surface of some sponge or some substrate that has the nanoparticles with the enzymes attached on it. So we acquire the ammonia ion, which is a basically charged ion, and this ion, in turn, in that sense, will change the potential of the electrode. So instead of the electrically neutral substrate, we acquire the electrical charge that basically affects the parameter of the electrode. And if we know how this reaction goes, and we know what type of potential will be equal to a specific calibrated concentration of the urea, that means that we can calibrate this particular sensor to the urea, and we can monitor this parameter continuously and within some system. The problem is that we need to make sure that the enzyme will be stable during the long-term exploitation. This article actually covers the stability of this electrode within a very long-term exploitation of this particular sensor, and they actually provide the information that this sensor can work in a stable manner within a few dozens of days without changing the accuracy of this system. And nevertheless, we are talking usually about the biotechnical system where we have to monitor urea for more than 5 years, because we expect the implantable artificial kidney working within the human organism. We at least have to adapt this system so it will work continuously for at least a few years, 1 to 5 years at the very least. That means that enzymatic method, despite of being promising method for that, and despite the fact that we can actually acquire a very stable electrode, we still need we have to be sure that this particular sensor will operate within at least within 1 year, or it would be even better if it will operate even within 5 years. So another idea that was explored by my student was to implement this cyclic voltammetry. Basically, the main idea is that we change the potential of the working electrode against the counter electrode, and we have the measuring system consisted of the working electrode and the measuring electrode, basically it's argentum, chlorine. And we observed how the form of cyclic voltogram changed in the presence of the urea. I apologize for this Russian language here, but basically this is the basic solution, a phosphate buffer that imitates the blood in terms of the pH and ion composition. And we acquired this the basic cyclic voltammetry just to understand how this particular solution behaves when there is no urea presence. And then we started to increase the urea concentration. So we had the cyclic voltammetry results for 5, 10, 20 millimoles per liter. And basically, if we go to the anode part of this cyclic voltammetry, we actually observe that there is a slight change of the current that we acquire from the surface of the electrode material. So basically, in terms of small concentrations, the cyclic voltammetry can be potentially applied in that manner, but there is a a very huge issue that we need to preliminarily calibrate this particular electrode. And another problem here is the electrode degradation. So if we talk about the long-term exploitation of that system, we can expect that if we utilize this electrode for a very long time without any calibration whatsoever, the surface of the electrode will be changed due to chemical reactions that might happen on these potentials. And if we change the cumulative surface area of the electrode, and if we change the composition of this electrode by means of any anode or cathode reaction, this composition will basically change the form of the cyclic voltammetry that we will achieve. So on the one hand, if we properly calibrate this system, we can acquire some response to the urea presence, but we have to take into consideration that we have to somehow provide a very stable electrode that chemically resistant to the media that we're going to work with. And another problem is the blood compatibility of the electrode. So we need to acquire the type of electrode that will be basically hemocompatible. And that's another issue with the cyclic voltammetry, because since we change the potential of the electrode, there is a big chance that at some point we will interact with the components of the blood. And we have to take into consideration that if we have the strong albumin presence, it could be an issue. So cyclic voltammetry is the potential method that can be used in terms of the biosensor application. It's more like just a sensor. This is a biosensor, but we have to take into consideration that multiple issues have to be taken into consideration when we work with that system. Just to summarize, to bring a quick summary of my lecture 9, in order to evaluate the adequacy of the renal replacement therapy in terms of implantable artificial kidney, we need to provide the online monitoring of the basic blood parameters. It could be the molecular parameters like the glucose concentration, urea concentration. We also have to take into consideration that we need to control the ultrafiltration flow. So what I did not mention during this lecture, that we need to acquire the type of sensors that will monitor the blood flow, the ultrafiltration flow within the microfluidic system. That's also a very essential part, because we need to imitate the glomerular filtration rate that has to be at least 120 milliliters per liter, just like it happens in the natural kidneys. That means that we need to provide the proper flow monitoring, and for that, this type of information can provide us the idea if this parameter will change and what exact phenomena that take place in the human organism will change this parameter. So we need to evaluate if it's just the heart rate that changes the ultrafiltration flow in the microfluidic system, or there can be some internal issues within the microfluidic system that does not provide the same glomerular filtration rate or the ultrafiltration flow that we're supposed to provide in that system. So we need to monitor the patient's parameters like the blood rate, and we need to establish the correlation between the blood, the heart rate, and the ultrafiltration flow that we create within the microfluid system. And we need to establish how the processes that take place within the microchip will affect the same parameter. In order to evaluate the clearance and the detoxification of the of the blood of the patient, we need to establish what kind of parameter we have to control primarily, what parameter is easy to control. And we need to establish a set of sensors that will allow us to recalculate some essential parameters like clearance, or it could be the parameter like KT on V, the parameter that basically shows us at what rate we clear the blood from specific substrate. And we need to control the nutrient concentration or the essential blood parameter concentrations. It could be the glucose concentration, or at some point it could be the iron concentration. It could be another challenge, because if we talk about the specific ions, we need to apply whether a method of specific conductivity measurement that will be an issue in itself, and or it could be a set of different electrodes that basically measure the such parameters as the sodium concentration or calcium concentration. But on its own, it's the issue that has to be resolved in terms of implantable artificial kidney, because when we talk in the perspective of the lecture that we had about the digital twin, we need to actually apply the machine learning for the digital twin to verify and validate this system to the implantable kidney. And for that reason, we need to collect some data from the implantable kidney. And for that reason, we need sensors as well. And basically, first and foremost, we need these types of sensors to establish a feedback loop between the patient and the doctor and the implantable kidney. And basically, we need to monitor how this biotechnical system operates within some very long time period. That's basically the end of my lecture. If you have any questions, I will be glad to answer them. Excuse me. Yeah, this lecture might be a little bit confusing in comparison with the previous day when we were talking about the digital twins, and people were more interested in that topic, apparently, considering how many questions we received that day. So to make a small link between this lecture and the previous day, since we talked about the problems of validation and verification, of course, the artificial intelligence is a very important topic. And there was a very correct emphasis that we need to think about the machine learning in that case. But the machine learning in case of the system, like the implantable kidney, would be a very challenging issue if we do not acquire any information from the implantable artificial kidney. So to connect those lections together, it's not just about the biofeedback for the doctor or for the patient, but basically this is a type of information that could be useful for the engineers and for the AI specialists who require this type of information to actually teach and validate and verify the digital twin. So basically, this is a type of information that will be required one way or another. In that case, of course, we talked about the feedback loop when we provided some information for the doctor, and there was the information received from the patient, and this type of interaction basically helps to evaluate the efficiency and the safety of the renal replacement therapy. Because if there is some critical issue with this apparatus, some emergency things have to be, measures have to be taken. Yeah, just like in this biofeedback concept. I mean, the feedback, like biofeedback is a very confusing term, and it actually, if you search for information about biofeedback, it could be mean a completely different thing from what we just discussed tonight. So I more prefer to see just a feedback rather than a biofeedback, despite the fact that we acquire some biological parameters from the patient, of course. Yeah. Mm.
So, in order to establish the feedback loop, we will need sensors in our implantable devices,
Mhm.
and obviously, we will need a wireless sensor network to communicate between the sensor and the patient. So, in that case, sir, do you think that the radiation coming out from the wireless sensors can affect the patient's health?
Yeah, that's a very, very precise and very good question, because we need a wireless connection to actually send the data to the smartphone or to the doctor. And we cannot just put a lot of wires in the patient in that regard. So that's exactly the issue that we have to address as well, the wireless uh, data link, that basically we need to evaluate. If we use some frequencies, we need to make sure that the radiation that different devices will um, produce during this data transmission will not heat up the internal parts of the implantable kidney. It will not heat up the tissue of the patient's organism. It will not affect the composition of those tissues. So on its own, it's a very complicated topic, and I think uh, some people can even formulate the entire election course just for wireless connection and wireless energy transfer. But basically, you're correct. When we are talking about the wireless connection and wireless data send link, we need to consider the safety issues, and we need to figure out if the wireless tools that we use in this feedback will not affect the temperature of the human tissues. It will not affect the temperature of the apparatus itself, because apparatus will heat up the external organs as well, and there will be no influence on the blood composition or any oncological issues that might occur if we use different types of the signal in that case. So yeah, that's a very good emphasis.
Thank you, sir.
Yeah.
Time in take outside and take tea and come back again at 12 o'clock tutorial lecture is there. Okay.